Hello, Pedro.
Hi,
Hi,
Pedro.
Keshab. How's it going,
Very
Benjamin?
good. Very
Hi,
good.
Pedro.
Well, I
Here
see
is Ariel,
Ariel.
Pedro.
I see Ariel as well.
Hi.
Good to see old friends.
How are you?
I am okay. We are, well, the COVID cases are declining in the US. So that's
Yeah.
good news.
Good.
And what about in your state, Keshab?
Yes, the cases are going down. But our
They're going down?
university
Okay.
is teaching remotely this semester. Means I can come and teach in the building, but students cannot enter. They have to take the class from their home.
Yeah. It's a big problem, huh?
It is harder, but it has gone well. It has gone well.
Yeah, a lot of Zoom.
And how are you teaching? Are you teaching remotely also?
Yeah. I took in my case, what I did is during the first semester of last year, I recorded the courses in Zoom. So the second semester, I did something different. I put the videos in YouTube and I told them, you have 4 days to watch the videos. And then on Friday, we'll discuss it. So I prepared a questionnaire and then I would prepare an example. So we would spend like 2 hours interacting. It was much more interactive than a regular class. So I actually tricked the students to spend more hours with me. I mean, part of them in YouTube and the other part in interacting. But it was very productive. We couldn't do any labs. I teach semiconductor devices, but we used a simulator, and so they worked a lot.
Excellent.
Yeah.
I like that. I like that approach.
There was no other option.
Okay. Pedro, we are on YouTube, and so
Good.
would you like to introduce Keshab or?
You go ahead. You do the honors.
Okay, 1 second. So Keshab Pahri, hello everyone, is from University of Minnesota. So he received the bachelor degree in the Institute of Technology on 1982, a master's degree in Pennsylvania, Philadelphia in 1984. The PhD is from California of Berkeley in 1988. Has been with the University of Minnesota, Minneapolis since 1988, where he is currently Distinguished McKnight University Professor and Edgar Johnson Professor of Electronics Communication in the Department of Electrical and Computer Engineering. He has published over 650 papers, is the inventor of 31 patents. He authored a textbook, very famous VLSI Digital Signal Processing System in 1999. His current research addresses VLSI architecture designs of machine learning system, hardware security, data-driven neuroscience, and molecular DNA computing. So Dr. Pahri is a recipient of numerous awards, including 2017 McVan Valkenburg Award and in 2012 Charles Desor Technical Achievement Award from IEEE Circular System Society. The 2003 in Kyoto, the Tomiyasu Technical Field Award and Golden Jubilee Medal from IEEE Circular System Society in 2000. He served as editor-in-chief in IEEE Transaction Sequence System, Part 1 during 2004 and 2005. He was selected fellow on the IEEE in 1996 and fellow of American Association in Advancement of Science in 2017. So it's an honor for us to have this distinguished lecture from Dr. Pahri, Professor Pahri. So please go ahead, Keshab, and we'll follow from here.
Well, good afternoon, everyone. And it's nice to be with you. And thank you to Pedro and all organizers for inviting me to be part of your conference. So I'm going to briefly talk about machine learning because that's very important today. So sometimes when we talk about machine learning, that is really signal processing. And so a lot of the things that we have been using to optimize signal processing algorithms can also be used to optimize machine learning architecture. So I'm going to spend some time talking about that. So let me share my screen. Okay. Can you see my screen?
Yeah.
Okay, great. Okay. I think, let me just see if I can get a pointer. No, okay, I don't see. Okay, so so there is always explosion of data. So these numbers are a bit dated, but still they tell the story. If you look at the amount of data created every day, that was in 2013 from the website at IBM, 2.5 quintillion bytes of data. And obviously that has gone up a lot more. Healthcare data continues to explode. Data from connected cars, smart cars, 4 terabytes of data per day from each connected car. And that means you multiply them by number of cars and number of days. So there is a tremendous explosion of data. And what are we going to do with the data? We are not collecting data to just record them and put them in cells. The whole purpose of collecting data is to process them and learn from data. And when we are learning from data, we are creating models. We are then using machine learning and artificial intelligence. Okay, so one type of machine learning that became very important since 2012 with the ImageNet contest is deep learning. And it all started with AlexNet and image recognition contest in 2012. So deep learning is now part of everyone's life. Google, Apple, I've listed just a few. Facebook, Amazon, Microsoft, IBM, Intel, Baidu, Alibaba, Tencent, but really it is impossible to list all these companies. And on top of this, there are hundreds of startups all over the world. So deep learning is everywhere. Okay, so what are people using deep learning for? I talked about the image classification contest that led to numerous deep learning models, 2012, 2013, 14, 15, and so on. And we'll get to that in a little while. Object detection, image classification, smart vehicles, smart cars. So there are so many ways of using deep learning in smart cars, whether there is pedestrian walking, what's the speed of the car in the next lane, smart drones, unmanned aerial vehicles, augmented virtual reality, robotics with intelligence, surveillance, biomedical healthcare, and the applications go on and on. And so I mean we can definitely say education is now very important part. So when people are learning on Coursera, for example, AI is grading the homeworks, and people are also AI is learning about what you are doing well, what you are not doing well, and so on. So so with all of that, so let me just have one slide here about this whole initiative in the United States called the national AI research initiatives. And so this is one particular program that's going to uh, allocate $160 million in a few months. And we will create 8 national institutes. Each institute will be $20 million. And so the NSF, US National Science Foundation, has um, created the topics of these institutes: human AI interaction, advances in optimization, advanced cyber infrastructure, computer and network systems, dynamical systems, augmented learning, advanced biology, and innovations in agriculture and food systems. There is tremendous interest in smart agriculture and smart food science. So that's another topic. And these are all the 8 topics. And so this competition is in process, and eventually at some point, maybe 5-6 months down the road, the winners will be decided. So I let me just say I didn't apply and I'm not part of any of these grant applications, but it's nice to know what the National Science Foundation thinks should be topics for all of us to pursue. So what was happening before 2012 is really traditional machine learning. So you get raw data, pre-process, segmentation, denoising, filtering. So all of that are pre-processing. Then we do some feature extraction. You identify features that could be temporal domain, like for example, peak magnitude or the energy of the signal and so on. And then frequency domain could be wavelet coefficients or power spectral density. And then we go through feature selection. I have identified, let's say, 50 to 60 features, and then I can rank them using the data and select maybe 5 to 10, for example. And then I can learn a model out of those 5 to 10 features. And then I ask myself, okay, how is the model doing? I have data that I divided into training and test. And if the test data is meeting the performance, whether the performance could be sensitivity, specificity, area under curve, then we are doing well, and that's great. So we have created a nice model that fits our data. And if not, if it does not meet the specifications or the desired sensitivity, specificity, or accuracy, and we go back in that loop and select some new features and then learn a new model and keep going through that loop until we have a model that satisfies our performance metrics. So what changed in 2012 in the ImageNet contest is the fact that in the ImageNet contest, AlexNet was able to outperform all prior techniques. And so AlexNet was proposed by Professor Hinton with his PhD student Alex Brzezinski. So this is a very old model. So it shows here that we are taking the input image and there are these images are of size 227 by 227. There are 3 images, red, green, blue, and we call them feature maps. So there are 3 input feature maps. And then there are 5 convolutional layers, convolutional 1, 2, 3, 4, 5, and 3 fully connected layers 6, 7, and 8. And if you look at below these numbers in the convolutional, the last number, the first 2 numbers are describing the size of the feature maps. At every stage, we are processing input feature maps, generating output feature maps. So for example, in convolutional layer 1, I took 3 images, 3 input images or feature maps. I'm creating 96 output feature maps. Those are then input to second convolutional layer. That then generates 256 feature maps. The third convolutional layer generates 384 feature maps, and then 384, and fifth convolutional layer 256. And at that point, we flatten those neurons to 4096 neurons, and the fully connected layers are connecting this 4096 to 96, that's 16 million connections, 16 million weights that will be trained to learn the model. And then there is a last layer. This was 1,000 class image classification. So the last layer has 1,000 neurons. And then we compute the probability that an input image belongs to one of the 1,000 classes by using a softmax activation function. So that's kind of the very basic CNN, so-called convolutional neural network model. And you can see that at any, what we see here is that the image size is going down. We started with 227 by 227, going down to 55 by 55, then going down to 27 by 27. So while the image size is going down, the number of feature maps is increasing. And then we flatten those number of neurons. Okay, that's kind of a basic characteristic of the convolutional neural network. And at each of these stages, you can think of there is a filter. Filter that is, for example, let's just think about what is the filter dimension to go from convolutional layer 1. Let's say I started with 96 feature maps, which was output from convolutional layer 1. And how am I going to generate 256 feature maps at the second convolutional layer? So you can think of that as 256 different filters. And each filter is going to be 96 filters of certain dimension, maybe 3 by 3 and so on. So you can think of this as these filters to be tensors. So these filters are now thought of as a 4-dimensional tensor, which is basically 96 3 by 3. Let's say the filters were 3 by 3 times 96 times 256. So that's a filter, and that's a tensor. Okay, so that's a brief intro to what is machine learning, what is deep learning. So I'm going to talk about 3 different topics that illustrate the ideas that I want to talk about. The first 2 ideas are really how do we reduce energy consumption by exploiting the so-called structured sparsity in the inference phase. So that's the first topic I'll talk about. The second topic that I will talk about is how can we reduce the energy consumption in training of these deep neural networks. We can always do inference. We can do that in the cell phones, and Apple smartphones and other smartphones have been doing that for a long time with face recognition and so on. But when we think about training these neural networks in the cloud, the energy consumed is enormous. So there is definitely great interest in reducing energy consumption of the training phase, which basically is the backpropagation, where we compute the error in the last layer, and then we backpropagate that all the way to the input layers and compute the gradients of those errors with respect to the activation functions and the weights. And those are then used to adapt the weights. So that's the learning the weights or updating the weights. Okay, the last part of the talk, I'm going to switch from deep learning to traditional machine learning. And I'm going to talk a little about a topic that I've been working on for about 10 years on seizure prediction using power spectral density features. And the goal here is to have implantable devices in the brain that can detect or predict seizures and then trigger deep brain stimulation. So it's a very low power implantable device approach that can trigger deep brain stimulation to desynchronize the brain activity and averts the seizures before it can happen. Okay, so how did all these so-called these names, Chinese names, Dian-Now, Da-Dan-Now, these mean supercomputers. So the inference accelerators for deep learning, and these are some early papers, 2014 from, let's see, this one is from S+, and the transactions in computers in 2017. So there has been work out of Chinese Academy of Sciences And after that, of course, there has been, so these are hardware accelerators. But apart from hardware accelerators, there of course have been GPUs. People, in fact, the ImageNet contest and the AlexNet could not have been carried out without NVIDIA GPU. So that contest, they used 2 GPUs to program the AlexNet. And then there has been tremendous progress at Google TPU, and these are workhorse of many things, all the way from natural language processing, language translation, and all kinds of things. And the Google TPU is now in its 4th generation. So they've already gone through 4 generations of TPU, and that's also, so they have separate TPUs, tensor processing unit, and that's basically systolic matrix multipliers. And so again, the systolic arrays that were developed in early 90s by H.T. Kung are now part of these TPUs. And there are separate TPUs for the training in the cloud as well as in the edge devices. Okay, this particular chip, Alibaba Hangguang 800, this is a data point from September 2019, and that claims to perform the most powerful inference chip, about 80,000 images per second, using the so-called ResNet 50. ResNet 50 is a deep learning model that has 50 layers out of Microsoft. ResNet stands for residual net, and it can classify 500 images per second per watt. Okay, so now what are the bottlenecks with respect to energy consumption? It turns out that deep neural networks are getting deeper and bigger. So that means we need more computations, but it's not really the computations. Computations are fine, but the real energy is consumed in accessing memory. And when I'm going to access memory from the, well, I'm not even talking about memory to fetch into the accelerator chip and buffer that. So I'm not really talking about DRAM memory, but inside the chip SRAM memory. So those are definitely the most demanding operations with respect to energy. And so it has been well understood. This is 25 years back when there was no GPU and no NVIDIA. And even at that time, people had understood the so-called memory wall problem, which means that 1,000 times worse performance and energy because of the memory wall. We have to go and get the data from memory. And that is still true. And so those working in digital signal processing recognized that as well 25 years back. And people doing video decoders, H.264 operating at 10 megabit per second. Again, same thing. It's not the video compression data path that was consuming more energy, but it was really the buffering of the data and memory access from SRAM that was consuming a lot more energy than the data path. Okay, so I briefly had alluded to some of these models. If you look at these models, 2012, AlexNet, the next BGG out of Oxford, and that became the winner in 2014. Then GoogleNet also became winner, and then a residual net out of Microsoft ResNet. And if you look at the number of convolutional layers, fully connected layers, started with 5 and 3, then BGG 16 and 3, GoogleNet 21 and 1, ResNet 151 and 1. So number of layers keeps increasing. Top 5 error given an image. Let's say the image is bird, some kind of bird. Now the AI system is going to guess, is going to say, okay, this image, input image likely belongs to, let's say, bird, let's say the bird with 45% probability, and with as a cow with 3% probability, and so on. So if the AI predicted model is the best 5, the ground truth is among best 5, then we say that the ground truth was identified correctly. If it is not in the top 5 probabilities out of the 1,000 classes, then we say the AI system has made an error. Okay, so the top 5 error went down from 16% to 3.5% with the ResNet. The last line is talking about how many coefficients do we need to train in these models. So they are anywhere from 50 megabytes to half a gigabyte, 500 megabytes. So definitely a lot of parameters to be trained. Okay, so this slide from Dr. Horowitz way back in 2014 describes the normalized energy consumption of memory access normalized with respect to a multiply accumulate operation. So the memory energy normalized to MAC energy multiply accumulate is 100 times for SRAM, 500 times for DRAM, and 1,000 times for flash memories. And that tells us that the energy, in order to reduce energy consumption, we don't really, of course, it helps to reduce number of multiplications, and that's where sparsity comes in. But more important than that, we need to reduce energy consumption in the memory access. Okay, so the convolutional, let's talk about the convolutional neural network. This slide from Bill Daly, who's at NVIDIA and Stanford University, and his PhD student Song Han, who was doing PhD at Stanford, now a professor at MIT, and doing many, many great things with respect to all kinds of things, applications, quantization in neural networks, reducing energy through all kinds of things. So the papers that he published in 2015 and 16 and during his PhD thesis, this whole sparsity. Sparsity means we can reduce energy consumption by simply reducing the number of parameters to be trained. So if you look at this fully connected layer to 6 to layer to 7, so 4,000 times 4,000, that's 16 million weights. And it turns out that if I just throw away 90% of those weights at random, so we will keep only 10% of the weights. That still leads to very good accuracy. So that's what is called sparsity. So throw away 10% of those weights. Sorry, 90% of those weights. So going from DRAM to SRAM, so this efficient inference engine EIE leads to 120 times energy savings, exploiting sparsity. As I said, throw away 90% of the coefficients, only train 10%, or in inference compute 10%. That saves energy 10 times, sharing the weights another 8 times, and out of the rectified linear unit ReLU, skip the zero activations. If it is 0, the input to the ReLU is negative numbers, the output is 0, don't compute anything, skipping that another 3 times. Okay. Evaluated on 9 benchmarks, EIE is 189 times faster compared to CPU and 13 times faster compared to GPU, and 24,000 times energy efficient compared to CPU, and 3,400 times energy efficient compared to GPU. Okay, these are really great numbers. To reduce the energy consumption by these factors is an enormous advantage. So we began looking at, okay, instead of throwing away 90% of the coefficients at random, what happens if I throw them away at not at random, but in some kind of sparsity? So these are basically saying these are random. So we don't really know where this is a sparse matrix used in low density parity check codes. But if you look at these LDPC codes that are used in wireless communication standards, wired communication standards, nobody uses the random LDPC codes, people use what are known as quasi-cyclic LDPC codes. And the parity matrix now has a specific property. You see these ones going cyclically, they come back and start here, then go down. And in the other diagonal here, these ones come down, then reset to the left side, then go down. So that's really what is quasi-cyclic LDPC codes. So how can we take advantage of that idea in exploiting regular sparsity instead of random sparsity? So to give you an example here, I have a neural network, let's say with 4 neurons in one layer, 8 neurons in another layer. So there are 32 connections. That would be called the fully connected network. Now we have a few numbers here and there. Many are zeros. And so this is called a random sparse network. Random sparse network. Okay. The whole idea of permuted diagonals network is simply this. So if I take the last 4 neurons in the output layer, they are connected one by one to the input neurons, these 4 neurons. And that's why this 4 by 4 submatrix. So think about this. We are computing an 8-dimensional vector, and this is 8 by 4 matrix, and that's being multiplied by a 4 by 1 vector, which contains the neuron values of these 4 neurons. And these diagonal connections are telling us that the last 4 neurons are simply connected to the corresponding neurons at the previous layer. And that's what I call permutation 0. I just begin with the diagonal values. In the top 4 by 4 submatrix, if I look at the 4 neurons at the from left to right, the first 4 neurons. So the diagonals are 0, but now I'm calling it a permuted diagonal. So I start with the diagonal values, I permute them with a value of 2. So if I start with this diagonal, shift right by 2. Start here, shift right by 2. Start here, shift right by 2. 1, circularly shifts back. 2, if I start with the last here, circularly shifts back 1 and 2. And that's what I call permutation value 2. So this 4 by 4 matrix is a diagonal matrix with permutation value 0. And this is a permuted diagonal matrix with permutation value 2. So this is a paper that we published in 2018 at the micro conference. What is the advantage of permuted diagonal matrix? In a random sparse matrix, I need to store the value. So for example, in this first column, I need to store the value 0.4. And where is 0.4? That's in 4th row. I need to store row index 4. Second column, 1.2. I store that value. And where is the number? Stored in row 1, so row index. So if each of these numbers takes qubits, then I have this P by P submatrix. So there are P values that need to be stored with qubits each, and P row indices with qubits each. Total memory space needed is a 2P words for 2P qubits. In the permuted diagonal, I still store these values, minus 1.5, 1.6, that's P qubits. But I don't store this row index anymore. I only store what was the permutation value. Is it 2? Is it 3? Is it 0? And these can be stored using log P bits. So we have essentially reduced the total number of values to be stored from 2P to P plus 1, and the number of bits to be stored from 2PQ to PQ plus log P. And I won't go through a lot of details that's in the paper, but essentially compared to the random sparsity, and random sparsity, remember, had this 34,000 and 2,000 energy saving factors compared to CPU and GPU. And on top of that, we are able to get another 3 to 4 times energy efficient um, energy efficient network. So by just reducing uh, by instead of having random sparsity, we now have regular sparsity. So 3 to 5 times higher throughput, 6 to 8 times area efficiency, and 3 to 4 times energy efficiency on different workloads. And so that's comparing the EIE, efficient inference engine, and the permuted diagonal network. Okay, so that's one example of how we can reduce the energy consumption by regularity in the neural networks. I'm going to switch gear and go to the second topic and talk briefly about the training process. The training process is many orders of magnitude more complex than the inference. And the energy consumed in training is enormous. So let's try to think about this is a fully connected neural network. And we are showing here a 4-layer network. This is a layer 1, 2, 3, and 4. So if you look at the bottom one is the inference phase. So we take the input and we compute the linear function W transpose X. W is the weight or the filter weight. The X is the input. Then we have an activation function. It could be sigmoid, tan hyperbolic, or rectified linear unit, and we compute A1. Same thing, activation output, layer 2, activation output, layer 3, activation output, layer 4. Okay. And then we have the ground truth. We compare, compute the error. Now the error propagates backwards where we are computing two different gradients. And we are computing these quantities called delta. So these are the gradient of the loss function with respect to these activation outputs. And we are computing this as G, which is the gradient of the loss function with respect to the weights. And finally, we need the delta and the G to adapt these weights of these layers. So two gradients need to be computed, the delta and G gradients with respect to the activation function, gradients with respect to the weights. Okay, so what is the traditional approach? If I computed these deltas one by one, so these are back propagating 4, going back to 3, going back to 2, going back to 1. So if I computed these and then computed these gradients with respect to weights, what will happen is I will be accessing memory a lot. So the whole idea of computing delta and G in an interleaved manner, as I will describe, is to reuse this delta so that I don't need to store that and bring that back again. So if you look at these equations, delta, the going to layer L minus 1, that's being back propagated, is the weight, it's a matrix multiplication of weight and delta. The gradient of error with respect to W, the gradient of with respect to weight is the activation times delta. So what we see here is this quantity delta is used to compute gradient with respect to the activation function. The gradient with respect to the activation function, that's this quantity here, as well as gradient with respect to weight. So the idea is, okay, when we have the delta, we use the same delta to compute both gradients, delta L minus 1 and this quantity called G. Okay, so that's really what we are doing. So the systolic, if we think about the systolic array to compute the gradient with respect to activation functions, that's a systolic array where the delta quantities from layer L are traversing from left to right. The gradients with respect to activation functions going to layer L minus 1, that's really delta L minus 1 collected in the systolic arrays in what we call weight stationary mode. Okay. While we are computing the gradient with respect to weight, those are computed in output stationary modes. So I take the same delta as previous layer, same delta. That's what I want to reuse. And I take the activation functions, these activation functions, Okay, these activation functions from bottom, and these gradients are being computed inside the PE. Okay, so the PE will compute inside the PE. In the previous one, the weights were fetched and stored, and this gradient delta L minus 1 keeps going up in the weight stationary mode. So the whole idea of gradient interleaving is these deltas, once they are fetched, they go through and stay here until I compute gradient with respect to weight as well as gradient with respect to the activation. So they stay there in the PE for 2 cycles. And so there is a lot of results that I'm not presenting, but this was published in the Circuits and Systems Symposium in the 2020, ISCUS 2020. And there are lots of results that basically shows we can get two to three times savings in the energy consumption by reusing the delta, and we are reducing memory access and reducing reducing energy consumption. So there are many approaches. So we don't reduce energy consumption by one approach, by taking many approaches together. Locality, using systolic arrays. Once you fetch the data, use it as long as you need so that you eliminate getting the same data back from memory again, reducing memory access. So the whole field of in-memory computing, this is a big field, and many specialists in many journals in IEEE and ACM in-memory computing. So instead of, as we realized, the memory wall is the bottleneck. Okay, why do I need to get the memory, get the data from memory? Let's go and compute inside memory. And then I don't need to, I can eliminate the memory wall problem. And that can be in-memory computing, started with SRAM computing. Now people are using in-memory computing for DRAM memories, flash memories, embedded DRAM memories, resistive RAM, and so on. So this whole field is exploding. Approximate computing, instead of all kinds of approximations, precision of the activation functions, quantizing those things, quantizing the filter weights. Binary A and N, the weights now are binary. They either exist or they don't, 1 or 0. Oh, they don't have to be binary. Instead of having 8 bits, they can be 2 or 3 bits. While I am back propagating the gradient, well, I don't have to use a floating point gradient. I can approximate gradient. For example, I can say, okay, let's approximate the gradient to be ternary. It's either -1 or 0 or 1. And so all kinds of approximations. I talked about sparsity, sparse interconnections, crossbar computing, memoristic computing. These are all variations of ideas in in-memory computing, which are, I didn't mention, but which are basically some kind of analog digital that are ideal for low SNR applications. There's a lot of interest in the spintronics, magnetic memories, materials, different materials, mixed analog digital. So the research field continues to explode. I talked about convolutional neural networks. These are great if we are going to exploit spatial properties to classify images. But if we have signals that have temporal properties, such as signals from time series, signals from drones, all kinds of signal processing applications, then the CNNs are not necessarily going to exploit the temporal properties. And well, language modeling, natural language processing, all of those are implemented using recurrent neural networks, RNNs, and the training algorithm in that is a variation called BPTT, backpropagation in time. So definitely there is interest in reducing energy consumption in training of the RNNs or reducing energy consumption in BPTT. Spiking neural networks, very nice work going on all around. There is work out of Zurich on dynamic vision cameras. Instead of processing every pixel, process only pixel where the change is happening. And Samsung is, and other companies are applying spiking neural networks ideas, sparse models, autoencoders, that became the foundation for GAN, generative adversarial network. The big thing today is really these transformers. When you think about natural language processing and translating from English to Chinese or Spanish or whatever, those are all done by these big, gigantic AI systems called transformers, spatial transformers, and sequential transformers, and so on. So, accelerating all of these for inference and training is a very, very active area of research. Okay. I'm going to briefly talk about the third part of my talk, which is this project that we started 10 years back. The goal was to predict seizures. And if you look at this a minute or so, 45 seconds to minute, the electroencephalogram shown here, the green part is when the person is seizing, and that's called ictal. There is the purple data. That's about 30 minutes before the person seizes, called pre-ictal, and then there is the blue data called interictal, or the baseline. So if I'm going to predict the seizure, that's a binary classification, which is purple signal versus blue signal. So that's called seizure prediction. If I'm going to detect the seizure, so that's another binary classification problem, which is the green signal versus the blue signal or the interictal. So ictal versus interictal is called detection problem. Pre-ictal versus interictal is called the prediction problem. These are two separate problems because the features that identify with or correlate with detection may not necessarily correlate with prediction. Okay, but from the deep brain stimulation point of view, prediction is more important because we want to avert the seizure and we want to have a prediction horizon of say 5 to 10 minutes, so the person can get a stimulation. So that way we can have closed loop neuromodulation instead of open loop neuromodulation. These are two examples of the data sets, the so-called University of Freiburg dataset that are 6 intracranial electrodes, and these are scalp electrodes collected out of Children's Hospital in Boston, part of the MIT PhysioNet dataset. So these are scalp bipolar electrodes. Bipolar means one electrode minus a reference electrode, and these are unipolar electrodes. And the first paper we wrote in 2011, we showed that computing the power spectral density and feeding them to a support vector machine with radial basis functions can get very high sensitivity. So these are the plots of the power spectral density. So if you look at the pre-ictal versus the interictal, the pre-ictal power is much higher in all neuroscience bands. And there are, these are the 6 electrodes, original electrodes. That's ictal, pre-ictal, this whole line is interictal. And this is bipolar electrode, so we take 6 and then get bipolar, 4 bipolar. And these are spatially, these are space differential, this is space differential and time differential. So this is just time differential and space and time differential. So in each and every case, the power spectral density is much higher for the pre-ictal compared to this interictal. And there is some power line noise here, which is 50 hertz. Okay, so while the sensitivity was great, what was bad was the false positive rate was 1 in 4 hours. So 0.25 false positives per hour, and that was not very good thing. So the paper that we published in Biomedical Circuits and Systems in 2016 basically showed that in addition to band power, if we compute the ratio of band power, that can correlate better to predicting seizures. For example, this is gamma 2 band power. So the gamma band is high band power. Gamma 1 band power is 30 to 50 hertz. This is 50 to 70 hertz. This is 70 to 90 hertz. And by themselves, these are the onsets of seizures. By themselves, they are not predicting necessarily This is interictal. But if we take the ratio, these all go high because at this time this is low, and this one going down, this is going down, the denominator going down, numerator is steady. The last one, both numerator and denominator going down, but the denominator going down a lot more than here. The slope is a lot steeper. So in each case, the ratio is amplified by the ratio feature. So why does that happen? And there is whole theory of that we published in the biocast transactions in a couple of years back. So the whole idea here is the theory is saying that if we take the filter transfer function from the pre-ictal and the interictal and normalize them, so there exists a band where the pre-ictal has higher power. There exists another band B2 where the pre-ictal has lower power. And if we take the ratio of these two band powers, that's going to be amplified. So that's kind of the reasoning behind why that happens. And using these, we showed that we can achieve very low false positives in this Freiburg dataset. This is the MIT, the scalp data. For these patients, we need only one electrode instead of 20 electrodes. Only one feature, high sensitivity, seizure prediction horizon, as small as 3 minutes, as high as 78 minutes. For other subjects, we need more electrodes and more features. For the Freiburg data set, for the intracranial, for a lot of the subjects, only one electrode and one ratio feature is enough, very low false positives. The minimum seizure prediction horizon is 16 minutes. Maximum is looks like 50 minutes. Okay, so that kind of shows that spectral features constitute a powerful feature set with reduced computational complexity and energy consumption. Few electrodes, few features, and simple classifier can lead to high sensitivity and specificity. Let me just say that this is a very difficult problem still and is still unsolved. In particular, I can create a nice model from 2-day recordings of the scalp data or 1-day recording of the intracranial data. But when I'm talking about the models that can hold steady for 6 months or 3 months, nobody has yet come up with solutions to that because the brain is highly non-stationary and models are changing constantly. And so still finding a robust, reliable seizure prediction for long-term continuous recordings. And I'm still working on that. And that's an unsolved problem. So last few minutes, I want to talk about several applications that are using deep learning. This is a paper from eBiomedicine out of IBM in Australia. And this was a clinical trial in Melbourne, Australia by Dr. Cook based on the device from the Neuro Vista company in Seattle, Washington. The company is closed down, and they had a 16-channel device that could be used to record data at 400 samples per second. And so the data from 10 patients using 16 electrodes. And this paper from IBM Australia shows that using deep learning. So now our feature maps to the deep learning are the spectrograms or the short time Fourier transforms. So if we create images from the raw data, feed them to the convolutional neural network, and then have a binary classification, and I compute the probabilities of belonging to interictal or preictal and get a probability. And that's the results are not very good, the classification results, but still this was one of the early papers to exploit deep learning for seizure prediction. So a couple of other applications in biomedical domain. So this is a paper out of Google published in Journal of American Medical Association. So the idea here was to take the fundus photographs from the eye, retinal fundus photographs, and grade these images with respect to diabetic retinopathy, who has diabetic retinopathy and who does not. And those who do, we can grade them as mild DR, mild diabetic retinopathy, moderate DR, and severe DR. Okay, so so there is publicly available data set as well as data set out of Berkeley, California. IPAX company that's collecting lots of data from patients in California. And very nice results. This is the Google Net that I talked about, using Google Net architecture, different layers, filter sizes, patch size is same as filter size, 3 by 3, 8 by 8, pulling. Um, and sensitivities are about 85 to 90%, specificities are 98%. That's really outstanding, because anybody who needs to go to an ophthalmologist first can be screened by a primary clinic doctor through this tool, and then identify those who need to be prioritized and sent to ophthalmologists. Uh, this is same people at Google again, but they took the same fundus photographs, but they were trying to predict the risk of heart attack and so-called hypertension. And so this is a paper out of Nature Biomedical Engineering in 2018. And so the whole idea is, why does a person get heart attack? Well, because the when person has hypertension, the vasculature or the vessels, blood vessels, uh, change in um, inside the eye, and that can be detected from the fundus photographs. So they were not only predicting heart attack, they were predicting a lot of other things: age, gender, blood glucose, HbA1c. And again, the results are not very good. If you look at the R squared values, 0.74, definitely the results are not very good, but still was one of the early papers to predict heart attack, risk of heart attack from the fundus images. The last example that I'm going to talk about is classifying what kind of arrhythmia it is from the single lead electrocardiogram of or ECG. This is not just saying who has heart attack or not, but classifying the 12 class: atrial fibrillation and flutter, atrioventricular block AVB, bigeminy, IVR, trigeminy, and all this, tachycardia, sinus rhythm. Okay, so 12 classes. So this is a company, iRhythm, out of San Francisco, and they partnered with Andrew Anga's class out of machine learning class at Stanford, and the Stanford cardiologists graded the electrocardiograms, and the students in the computer science class modeled, created the model using deep learning. So 33 convolutional layers and a linear output layer that has 12 neurons in the output layer, classifying 12 types of heart attack classes. Okay, so single recording, single vector, 200 hertz recordings, 91,000 single lead ECGs from 53,000 subjects. That's training set, tested on 328 recording from 328 subjects. And again, this outperformed, the model outperformed the best trained cardiologists from Stanford. This is a paper published in 2019 in Nature Medicine. So I have gone through a few ideas in reducing energy consumption, and I've talked about a few applications of the AI systems, particularly deep learning systems in some biomedical, but at least that gives a brief idea of how this field is exploding and will continue to explode for next couple of decades. Reducing energy consumption of traditional machine learning systems requires clever ranking of features and creating these models and all kinds of approximations. In the deep learning, so-called neuromorphic computing, we also require many forms of sparsity and approximate computing, and brain-inspired computing in many forms. Deep neural network, recurrent neural network, convolutional recurrent, and spiking neural network, all of these will continue to remain prominent for many, many years to come. Okay, so that concludes my talk. I am happy to take a few questions.
Okay, if you don't mind, I can go ahead. I have one comment and one question. I'll try to not forget because it's already pretty late here in Europe, so my brain is in low power mode. But one thing, you know, there's one clear message after your talk, and is that reduce the memory. The more memory you have, the worse it gets, and these deep neural networks require a lot of memory. So one interesting thing that I read at some point was that they didn't allow every single value for memory values. So they picked a number, let's say, I don't know, 20 or 40 possible values for the weights, and then they rounded up everything to that. So that was one clever way to reduce things. So that's the comment. And the question that I wanted to ask you was, what about on the technological level? What do you think could be the most promising technology to help in this direction of making it easier for RAM memory storage and energy?
Well, thank you, Pedro. Your comment is well taken. I think so. When we have let's say we have three possible values, I can, or say four possible values, then I can have a 2-bit to grab those four possible values, and that's certainly true. In terms of technology, you know, I think well, there are so many things happening. I mean, if you look at technology node evolution, and TSMC is now talking about 3 nanometer nodes. So they continue to progress well. And that means the technology is the technology scaling according to TSMC is very much alive, and they continue to go down to 3 nanometers. So that's certainly good. So many things really, I mean, in terms of tools. So a lot of the companies are bringing out high-level synthesis tools. So that means now it is possible to take your Python code and get characteristics about memory size, energy consumption, those kinds of things. That's great for, so there are publicly available tools out there, and lots of people in the US are working on them, whether it is out of University of Washington or Zero Zhang out of Cornell, out of Georgia Tech. And so if students are writing papers and they want to compare 3 different neural networks, they don't necessarily have to write Verilog codes. The Python code will give them results for these models in terms of area, memory, energy consumption. And then there is a tremendous progress in democratizing Python code for whether it is PyTorch or TensorFlow. So I think a lot is happening. That doesn't mean that it's easy. That doesn't mean there is no learning curve. But for students to jump into these things and learn, I think it can be very quick. So technology, tools, both are evolving rapidly.
Yeah, that's true. That's true. A lot of things going on. I would be very interested, Keshab, if you could, that link where you mentioned that with Python you get estimates and avoid all the hassle of describing the entire network in Verilog. If you can send a link or two, that would be great.
I will do that.
Okay.
I have a question about the systolic array, right? Did you test this idea about the systolic array in GPU and ASIC designs or FPGA to validate this idea about the low energy backpropagation accelerator? Or where you test or implement this algorithm?
Well, thank you, Ariel. And this is a good question. I mean, the backpropagation savings have to be validated. Yes, we did. So Nanda Unnikrishnan, who is my PhD student, did the work. He wrote a emulator to map these into different sizes of systolic arrays, 128 and 256. So he played with many different systolic array sizes, many different batch sizes, and there's a lot of results that he obtained. Unfortunately, as you can expect, they are not in the Circuits and Systems Symposium paper, but we are about to submit a journal paper, and that should be in that paper. So I certainly would be happy to send you a copy of that paper. The paper should go out within a couple of days. So it's ready,
Okay.
so I can send it to you.
Okay, thanks. I don't know if any more questions.
I have a question. Hi, Keshab.
Yeah, hi.
Thank you very much for the talk. It was very interesting. It was a lot of information. I saw a punctual theme that is part of my work in some place, related to the compressive ANN. If you know if the compressive ANN shares the principle of the compression sensing, for example, for image sensing, because it's, the slides says that compressive ANN, I don't remember very well, sparse interconnections. Compressive ANN implies random selection of samples. If you want to apply this principle to ANN or interconnection, you have to select random interconnections. Is that the meaning of the compressive ANN?
Yes, thank you, Nico. Yeah, so random sparsity means selecting at random. So randomly select 10%. But we are not really, we are having a sparsity that has certain structure. So that means now the permutation values. So what should be the value of P? So that micro conference paper in 2018 describes the different values of P for convolutional layers and for fully connected layers and the permutation values. So those have to be used in the training process as well. So so there is some optimization going on to select the right P and the right permutation value during training so that the performance is acceptable. But yeah, I mean, I don't think we can really say it is compressed sensing, although compressed sensing is trying to achieve same thing. So, well, I mean, I think we can say that this whole training process, the backpropagation is applied on the permutation value that we select. So we are updating just those weights. Those, think about the stamping those locations and updating weights at those locations during backpropagation. So we are only updating those weights.
Okay, I understand. Thank you very much.
Thank you.
Okay, I think, any more questions? Okay, I think that it's all. Thank you for your time, and it was a very, very interesting presentation. So thank you for your time, Keshab. It's a pleasure.
Well, thank you, Pedro, Ariel, and all the people here. Thank you very much to all of my friends in Argentina and whoever is attending the conference.
Thank you, Keshab.
Thank you.
Looking forward to having you in Argentina in presence when we get rid of this pandemic.
That will be great. Thank you.
Yeah. Thank you so much, Keshab.
Thank you. Thanks
Bye.
so much. Bye-bye.
Bye.
Thanks. Bye-bye.